Green light?
No, I think you muted it.
How about now?
Good.
I think I just put it in my pocket.
Yep.
All right, well, thank you for everyone for coming, and yeah, I can definitely hear we're on now. Saturn is one of the most beautiful and dynamic objects in the solar system, and of course it was known to the ancients. So what we're going to do today is we're going to take a journey, it's a historical talk, with a little bit of science thrown in here and there, a journey over the 5 centuries of a single question, which is what is the day on Saturn? So the title of the talk is 17th to 21st century quest to find Saturn's rotation period, the day on Saturn. William Herschel, one of the most famous planetary astronomers of all time, who discovered the planet Uranus, which was the first planet to be discovered since the ancient times, said about Saturn in 1805, "There is not perhaps another object in the heavens that presents us with such a variety of extraordinary phenomena as the planet Saturn." And well before we had telescopes, and they were invented in the 1600s, astronomers studied what they called the 7 celestial orbs, and this is how it was spelled, with the AE and the long S, almost unreadable, and that's only going back 5 or 6 centuries. Saturn at that time, before telescopes were invented, got its own day of the week, Saturday. And of course we can fill in the well-known English names for the 7 days of the week, and there are 7 orbs in the sky and 7 days of the week, and they're all named after the orbs in the sky. It's a little easier to see that, to trace that, if you ping pong between the English and the French. English comes from Old English, which is Germanic, and French is a Romance language coming almost directly from the Latin. And so we're going to do a little ping pong here. We start with Sunday, which is clearly Sunday, the day of the sun. In French, it's actually Day of Our Lord, so it's Dimanche. In English, and my French is mangled, it's three years of high school French. And then we move to Monday, which is clearly Moon Day, and also in French, Lundi, which is lunar day. So it's very clear that that day is the Moon Day. Then we get a little kind of strange with the tracing the etymology in English, but in French it's very clear. The next day is Tuesday, named after the god Tu, but in French it's Mardi, and very clearly that's Mars Day, and the god Mars and the god Tu were actually related. Gods of war. And then we have Wooden Day, which is obscure. So we have Wednesday, but in French it's very clear, it's Mercredi, and Mercredi is Mercury Day. And then we have Thursday, or Thor Day, which in French is Jeudi, which is Jupiter Day. So Thor is kind of a minor Jupiter, but both gods of thunder, and those are related. And then we finally have Friday, which is Frigg Day, and again, obscure. But in French, it's clear, it's Vendredi, it's Venus Day. You can see all these celestial orbs in the sky. These were what were known to the ancients before telescopes were invented. And finally, we get back to the weekend, and we have Saturn Day, which in French, they switched to call it Sabbath Day, like the Jewish Sabbath, Saturday. But the scientific question is that now spanning 5 centuries, that is the main topic of today's talk, is what is the length of the day on Saturn? The question actually can be traced back scientifically to the 17th century, that's the 1600s. In a brilliant series of observations, Cassini found surface markings on both Mars and Jupiter and determined their rotation periods. That was 1665 and 1666. This was the age where telescopes were being invented and perfected. But Saturn was a much more difficult subject. Cassini, the person, the scientist, we'll talk about Cassini, the spacecraft, and we need to distinguish those. But Saturn was a much more difficult subject. He could not make an actual determination. He tried. So we'll count that this started in the 1600s. These words are from astronomy historian Van Helden, from a paper he wrote in 1984. The first actual value for the rotation of Saturn came in the late 18th century. William Herschel finally managed to determine a rotation period. Late in 1793 and early in 1794, he kept careful track of small irregularities on what he called the quintuple belt and deduced a rotation period of 10 hours, 16 minutes. So we have our first dart on the board. Also in 1794, just to get a sense of how long ago that was, Kentucky and Vermont both got their stars and their stripes on the Star-Spangled Banner, on the US flag officially. This is the actual Star-Spangled Banner itself, the one that inspired the national anthem. And this is the actual flag that inspired the national anthem a few years later during the 1812 war. As it was flying, it was designed to be seen from miles away, and it's called the Great Garrison Flag of Fort McHenry. And you can count, there are 15 stripes. It's the only flag in United States history that actually went up to 15, and it has 15 stars. So Vermont and Kentucky, at least for a brief period of time, Kentucky had its own stripe as well as its own star. That was 1794. Also in 1794, to give you perspective, Eli Whitney patented the cotton gin, and this is the actual patent application. So that's where we start with our first actual measurement. And I have a paper here, which is not showing very well, on the rotation of the planet Saturn. This is actually a photograph of William Herschel's paper, and I love the title. This is, again, from the 1794, On the Rotation of the Planet Saturn Upon Its Axis, an entire scientific peer-reviewed paper, the first one to come out on this subject, and that was the only topic of this paper. And he wrote, in a late paper on the multiplicity, so you can see how they do it, William Herschel and all of his titles, and then red, they always said red, January 23, 1794. In a late paper on the multiplicity of the regular belts of the planet Saturn, I pointed out an analogy which might lead us to surmise that it had a pretty quick rotation upon its axis. I can at present announce the reality of that rotation. The following series of observations in which Saturn has been traced through 154 revolutions of its equator will suffice to confirm it. What I'm going to do with these historical papers is basically show you the first sentence and the last, and kind of skip to the conclusions without the intermediate part. And so at the very end of this paper, he says, and after we had shown, look at how shown is spelled, S-H-E-W-N, that a proper motion in the spots of the belts of 116 degrees one way or of 117 the other would only occasion an error of 2 minutes in time, a 2-minute error bar. And you'll see when we get to the 21st century, we still have a 2-minute error bar, which is just astounding. We need not hesitate to fix the rotation of the planet Saturn upon its axis at 10 hours, 16 minutes. William Herschel, Slough, near Windsor, January 23rd. All right, so that's the first shot on the board. And here we go. What I'm going to show you now is just the list of the names. It's like a who's list of astronomers. These are the Saturn rotation period astronomers. And several astronomers not on this list, and that's just for space and convenience. There are several astronomers that contributed, but these are the key ones. And you'll see the enormous gap in the 1800s between Herschel and the next one we'll talk about, which is Hall. But then it's just incredible. You have Williams, Keeler, Flammarion, Barnard, Phillips, Lowell, Butterton, Haas, Osawa, Reese, Haig, Moseley, Sanchez-La Vega. Now we're getting personal. I know Sanchez-La Vega. That's Augustine. He's in Spain, and we've been on papers together. And then, of course, the entire Pioneer 11 team will start with the spacecraft age. See how late it is in the quest here. And then Voyager 1 and Voyager 2. Notice how close Pioneer 11's first encounter with Saturn, that was the first spacecraft to get to Saturn, how close that was. It was only a year before Voyager 1, which was just a partial year before Voyager 2. And then we had a little wait, and then we had Cassini, which was an amazing, amazing flagship orbiter that lasted 13 years. Okay, that's the list of all the various people that have worked on this particular subject of what is Saturn's rotation period. All right, so we know from the very first shot on the board from 1794 that it's somewhere in the 10-hour and change. 10 hour and 16 minutes was what Herschel was not hesitant to declare. Here are all the other ones, and it's almost buckshot. It just sprays out, and you'll see trends. There's a trend here early in the first couple hundred years, or the first decades anyway, right? Trend, and then a huge jump, which was a huge surprise. And then as we get into the 1900s, the 20th century, all over the place. And then there's kind of a consensus up high, and then you see in the last 10 to 15 years, it's dropped down again. So we just can't make up our minds. And so what we're going to do for this talk is we're going to trace the history and the various things that we have been learning during this time. Okay, so I will point you out kind of the end result where we're heading with this, is that we do think that there's a modern convergence just in the last, since about 2009, to 10 hours, 34 minutes. And you can see all through history that that number had never really come up before. But we've had two independent analyses based on waves that I'm going to talk about at the end of the talk that are both getting 10 hours, 34 minutes completely independently. And then another study that uses a different method that's also getting very close to that number. And this is not the official rotation period for Saturn. The official rotation period for Saturn is way up here at 10 hours, 39 minutes, 24 seconds. So that's what we're going to talk about. This is a fascinating history of astronomy that spans these 5 centuries. Okay, so we're going to look at 10 milestones in the quest since the first milestone, which was 1794. And see what we can learn about Saturn itself and about this incredible, unbelievably difficult measurement of a primary fundamental property of a planet. So these are the dates, and as I go through the talk, I'll be highlighting each date as we get to it. We're going to jump all the way from 1794 to 1876. There's this enormous gap here, and then these are not just observations of Saturn, these are also theoretical developments and so on, as you'll see. Okay, let's start with this huge gap, an 8-decade gap between Herschel's successful first measurement and the second one that tended to confirm it. This was Hall, and the slides are different than I laid them out. There we go. Hall, and I'm going to just quote him. It seems that during the 19th century, and I'm quoting this historian here, no one had been able to observe any spots sufficiently to make a like attempt, like Herschel, until 1876, when American astronomer Asaph Hall succeeded. And this was the year before he became renowned for the discovery of the 2 satellites of Mars. This is words of the astronomy historian Alexander, who published this book called The Planet Saturn in 1962, which coincidentally is the year I was born. What I love most about this talk and this subject is you can lay astronomers' careers end to end to end to end across the whole thing. It's just incredible. At least 5 or 6 careers wide is this quest. By then, Herschel's value had been forgotten. Not too surprisingly. Over a lifetime since Herschel's value had been established, and it was not known to Hall and the other astronomers. It was not in the current ephemeris they were using. So Herschel's value had been forgotten, and the ephemeris was based on a ring rotation value by Laplace, which was, quote, worse than useless, because an error of over 13 minutes would be quite sufficient to make all attempts to observe the spot in transit on subsequent dates miscarry. So Hall, as soon as he saw this great spot, he communicated it to his colleagues in astronomy, and they had the wrong ephemeris by 13 minutes, and yet Hall persevered over the next year and a half and obtained a value of 10 hours, 14 minutes. That's without knowing Herschel's value. He had to overcome, add 13 minutes to that, he had to overcome an enormously wrong ephemeris to get back to the value that Herschel had done over a lifetime before. Okay, so that's on the board. And then we're going to not have any gap quite that big anymore, but we go now to 1895. It's still 2 decades. And this is where the first confirmation came. And this is exciting because instead of looking with the naked eye through the telescope, we now bring in a new instrument. And this is good astronomy history because this instrument is the spectrograph. And the spectrograph is, to this day, one of the most powerful things you can put at the end of a telescope. So confirmation came 2 decades later. Keeler used a spectrograph to get the rotation speed via the Doppler effect. And the incredible power of the Doppler effect was just becoming appreciated across the astronomical community. So this is in 1895, and look at the nut value. It's very similar. It's very, very steady. Here, let me show you some of the data. This is the paper itself from Keeler, 1895, a spectroscopic proof of the meteoric constitution of Saturn's rings. And in this case, meteoric, this context, it means simply made up of many small parts, not a solid ring. When you look, they called it the ANSI. These were the sides, the rings. We had no idea what they were. Were they solid? Were they made up of small particles? A couple of years earlier, it had been proved mathematically that they couldn't be a solid object, that it had to be small particles, but there hadn't been any physical proof of that. That's what Keeler provided. So this is actually one of the key milestones, not only in the search for Saturn's rotation period, but for astronomy itself, showing the power of the Doppler effect and of spectroscopy. This is a sample of the data that he took from his photographs, and I will be circling a number there in a minute. But this is a figure 1 from the paper from 1895, and you can see here that there is the Doppler shift being measured and lined up with the planet itself, and on the edge of a planet we call that the limb, and also the rings. And what you notice when you analyze this is that the inner ring here is rotating faster than the outer ring because it's lifted up here on the Doppler shift. Faster. Now think about it. The competing hypothesis is that the ring may be a solid object, an enormous solid object around the planet. In that case, it would be like horses running around the Kentucky Derby or cars going around a NASCAR track, where the cars on the inside and the cars on the outside are keeping the same angular velocity, so they're keeping the same line as they go around. What does that say about the outside cars? They have to be going furiously faster. And the inside cars have an advantage. They can go slower, but still keep the same angle. Okay, that's solid body rotation. You would see the inside moving slower in meters per second, miles per hour, kilometers per second, however you want to call it. You would see this slope the other way. In fact, it doesn't. The inside of the rings is faster, and that's what we call Keplerian shear. That means you have small particles orbiting the planet rather than a solid object. So that was the first time this had been proven by a physical measurement rather than just deduced as most likely. Also, we have the fact that the ring is sheared across here. And then when you get to the planet itself, we can put a number, a fairly accurate number, on the actual speed of the planet's rotation. The equator is rotating at 10.3 kilometers per second, and that number here on the data table is right here. Velocity of the limb is 10.3 plus or minus 0.4 kilometers, and the per second is applied here. So you can see that we have, for the first time, a physical measurement, and that was using the newly appreciated Doppler effect and the new spectrographs on telescopes. Okay, so this confirmed this number of 10.3 kilometers per second actually comes out to be the same as what the other astronomers had been finding for Saturn's rotation period. The one obtained by Hall, which turned out to be the same as Herschel. Okay, so that puts us down at the bottom here. Then we go forward to 1903. So from 1895, where the spectroscope was brought into play, to 1903. And what you're waiting for on Saturn is something you can track. And there was an enormous outbreak in the 20th century, right at the beginning, in the year 1903. There was an outbreak of bright spots on Saturn. And intriguingly and interestingly, instead of being on the equator or near the equator, they were in the north temperate area, basically like Louisville latitude. They were in the mid-latitudes, well north of the equator. That means we're sampling a different latitude, and that's very exciting. And what value for the rotation of those spots was obtained? It was much, much longer. Look at the jump. In 1903, we jumped all the way up to 10 hours, 38 minutes, which is ridiculous because there is no way a planet can change even a fraction of a second over millions of years. This is a very stable parameter of a planet. What is its rotation period? But clearly what we have here is shear. We have jet streams. We have different latitudes moving at different speeds on Saturn. So that is an absolutely huge gap. Now keep that in mind because that's very close to what the official Saturn rotation period is today. The official period is 10 hours, 39 minutes, 24 seconds. And we now know, as you'll see as we get towards the end of today's talk, that that period is not the rotation period of Saturn. The official period is rubbish. It's not the rotation period of Saturn. Okay, but then we jumped up to it. So what's going on? Well, the British amateur astronomer Arthur Stanley Williams, and most of these observations, even today, are amateurs and often are organized by the English, the British. They've been doing this for centuries and doing it very, very well, very soberly. They have day jobs, but they're astronomy, they write the books, it's just incredible. So this is one of them, Arthur Stanley Williams. He did a lot of observations, but he also did a lot of the history of these things. And he's the one that coined the phrase belts and zones. And that was in 1898. He said of Saturn's 1903 spots, it seems clear, therefore, that we have on Saturn, as on Jupiter, a great equatorial current having an enormous velocity in the direction of the planet's rotation relative to the extra-equatorial surface material, what today we would call extratropical. But the velocity of this current on Saturn is almost incomparably greater than on Jupiter, amounting, as it does in miles per hour, to between 800 and 900, as compared with the 250 miles an hour of the latter planet. This is the latest and greatest jet stream profile versus latitude of wind speed in miles per hour of Saturn in yellow and Jupiter in red. And you can see that, and this is obtained, both of these were obtained from the Cassini spacecraft, which is shown here. And so this is our best measurements right now, and you can see that each planet, unlike Earth, which has only a couple of jet streams, has dozens of jet streams, and they're very similar, but that Saturn just completely dominates in speed. And the number was 800 to 900. The modern value is very close to 800 for the equatorial current, what we would call the equatorial jet. And Jupiter also has a strong equatorial jet, but it's way down here, and remember the number that was quoted was about 250, right on. There's 300, there's 250, it's right on. So it's incredible. What we've filled in with the spacecraft, of course, are these details. But over this, especially over the 19th and 20th century, we were able to get the sense of this enormous equatorial jet and the fact that if you're at different latitudes, you're going to get different rotation periods. So what is the actual bulk rotation, the fundamental bulk rotation of Saturn? That's what we're after, and that's what we still are working on. Okay, so let's go now to an astonishing little blip of a notice by the famous Percival Lowell, famous for many things. This is 1916, and Percival Lowell wrote a little paper, a little theory that he just had, almost an afterthought, just a little theory. In the astronomical publications, it was a mention is made of this in 1916, and I want to read it to you. They had these little paragraphs, and each paragraph would be one of the planets, and they were basically what's the news of the day on this, observing these different planets. And this one is the rings of Saturn. They say, Professor Percival Lowell, he's not talking about the rings, he's talking about the planet in this first paragraph. In a recent publication, comes to the conclusion that Saturn is actually rotating in layers with different velocities. Not latitude, I'm talking about inside the planet. The inside one turning the faster. If these layers were two only, or substantially two, this would result in Saturn's being composed of a very oblate kernel surrounded by a less oblate husk of cloud. And the original, which I haven't actually traced yet, but I'm still looking for it, is in the Lowell Observatory Memoirs, Volume 1. This appeared in 1916, 9 decades before the Cassini proximity orbit results that I'm going to end the talk talking about, the latest and greatest billion-dollar results from Cassini. Lowell's layer theory will prove to be uncanny. All right, now what can you learn from rotation? Why is rotation so important? Clearly one of the parameters, along with size, density, one of the bulk parameters of any celestial object. Let's consider that we have two giant planets and they're both rotating. When a planet rotates, a fluid planet particularly, but any planet, when it rotates, it throws itself out, it becomes oblate from the centrifugal acceleration. All right, these two planets that we're considering are basically twins. They have the same mass. They have the same size, and they have the same shape. Therefore, they have the same bulk density. But there's one difference. The one on the left is rotating faster. And the point here of playing this game is that with Saturn, we're not knowing its rotation period, its bulk rotation period. We don't know which one Saturn is. Is it the left planet, or is it the right planet? And if we think it's the right planet, and it turns out that we're off by 5 minutes, which it turns out we are, then it's going to throw us over to the left planet, and it's going to completely change something. And I want you to think. What is it that it's going to change? What can we learn by adding rotation? So that's the question. What critical scientific question does rotation reveal? It's almost like an X-ray. It's such an important number to know. This is putting emphasis on the motivation for this whole quest, this 5-century quest. We don't know this number, and what is that? How are we getting killed by that scientifically? What is it like? It's like an X-ray. So I'll take questions or answers from the audience. Anybody? We have a little skeleton audience here. Anybody want to hazard a guess? What do you learn about these two planets? They have the same mass, same size, same shape. One on the left is rotating faster. What can I say about the inside of the planet? Any ideas? The internal mass distribution. In order to have the same shape, if your mass is concentrated closer to the center, you're rotating faster. Because if you took some of that mass from the center and moved it out, it would make your planet even more oblate. Remember, if you're swinging around like a skater and you pull in your arms, it affects your rotation. So we know that the planet's rotating faster, has to pull some of its mass in, has to be more concentrated towards the center. We get internal mass distribution simply from knowing the rotation rate. And not knowing it means we are really struggling on the internal structure of Saturn. Now this is a simple version of this, and this would be correspond to what we call J2, which is the first even harmonic of the gravity field of Jupiter. What Cassini has done with its 13-year mission towards the end with its proximity orbits, the last 26 orbits, was to get those gravity harmonics up as high as possible. It's like a Taylor series, to get those terms. And we're just talking about J2, J4 here, and not even, and we're still uncomfortable at that level because of the incredible structure that we're discovering on the inside of Saturn from the gravity measurements. But that's what you get. You get internal mass distribution. It's very sensitive to rotation. Okay, so that brings up the interior, and clearly that's the big story and the big takeaway from today's talk is how incredible the interior of Saturn is and how much is going on that we're just getting a sense of. So we can ask, what about Saturn's magnetic field? Every planet that's rotating and large enough has, like Earth, has a magnetic field. And in every case, they are tilted. And so you just fly your spacecraft by the planet and you get that wobble, that tilt. This is what we did for Jupiter, what we did for Uranus, what we did for Neptune. We can do it for any planet. We can do it for Earth very nicely. You get that little dipole tilt swinging around, and you get the day very nicely from that. Okay, what about Saturn's magnetic field? Well, we couldn't observe Saturn's magnetic field. We're doing this chronologically, and we're still down here in the 1930s. What happened was a theoretical development, and the theoretical development was not based on Saturn, it was based on the sun and observing the surface of the sun and the surface sunspots, which had been known for many, many decades, and were being, at the time in the 1930s, analyzed for their magnetic structure, their magnetic properties. So in the early 20th century, the planet's magnetic field, Saturn, was not yet observable. That took spacecraft. Unlike Jupiter. Jupiter, you can actually see radio emissions coming from Jupiter that are very noisy. In fact, when they first laid wires, almost like a clothesline, to start looking at some of the celestial radio signals back in the early days of radio astronomy, they had this huge noisy signal, and it turned out to be Jupiter. In fact, if you could see Jupiter's magnetic field in the sky, it would be the size of the full moon. Saturn is much further away, twice as far away as Jupiter, and its magnetic field isn't quite as strong, and we just can't really decipher the magnetic field structure from Earth, at least at the time, in the 1930s. But we could see the sun very nicely in the sunspots and some of the structure in the sunspots and the sunspot cycle. And they were being heavily studied. And this motivated Dowling, no relation to Dowling, Dowling's theorem, which is a very famous theorem in magnetohydrodynamics and in what's called dynamo theory. This is 1933, and this is the original paper. The magnetic field of sunspots by T.G. Dowling. And he starts, it is well known that a magnetic field is a characteristic property, lists the properties. And this motivates him in this paper to say, let us therefore consider under what conditions a steady magnetic field can be maintained. A steady magnetic field can be maintained by the currents it induces in an ionized gas in steady motion in it. That was the beginning, and then he works through the argument, and his conclusion is, a contradiction has thus been reached. We conclude, therefore, that it is impossible that an axially symmetric field shall be self-maintained. You can't have a perfect field that's actually symmetric, that means around the belly of the planet, with no tilt. You cannot have a no-tilt magnetic dynamo sustain itself. It's impossible. This is called Dowling's theorem, and it's been known since 1933, so that's what, 80, going on 90 years? Okay, so Dowling's theorem is very well documented and verified. And so we expect every planet to have a tilt to its magnetic field, so no problem. You get the spacecraft there, you measure it. The implication is that a planet's magnetic field dipole, magnetic dipole needs to be tilted in order to actually survive and exist. Okay, so that's great news. That means we're just going to have to get our spacecraft out to Saturn and we can solve this problem. In the mid-20th century, before spacecraft started to fly, we have numerous observations refining the profile of Saturn's winds, that great equatorial jet. And you can see they're all over the place, but that's because we have that 800 mile per hour equatorial jet. And this was being worked out by quite, you can see now it's getting quite popular. The astronomy, Saturn astronomy is all over the place, and this is being mapped out. And it's not, and people understand that there's not just a single number for the atmosphere, that there's this whole equatorial jet, and that was being mapped out very nicely. And then, of course, the observations became quite furious just before Pioneer and Voyager were coming, just as ground support, we call it. And then interplanetary spacecraft began to fly. The first spacecraft to encounter Saturn was Pioneer 11. There was Pioneer 10 and 11. 11 went to Saturn, and the encounter was in September of 1979. This is actually a little image of Pioneer 11. They only recently stopped talking to Pioneer 11. And so you can see where we're at in our chronology here. We're now in the modern era. Spacecraft exploration has started. And frankly, if you go back to the 60s with the first Venus and Mars encounters, the spacecraft exploration's been going on since the late 60s, and it's finished its first half century and it's entered its second half century. So this is 1979, our first close encounter with Saturn. There was a beautiful magnetometer. That's this long boom here. Every one of these spacecraft that go in the outer solar system, you see this big, long magnetometer boom. That's to get the sensitive magnetometer away from the tape recorders and the other electrical devices on the spacecraft to minimize the noise coming from the spacecraft itself. So we had a beautiful magnetometer here, and Pioneer 11 was able to establish that Saturn magnetic field is tilted less than 1 degree from the rotation axis, and they could not get a rotation period. And that was astonishing. That was incredibly unexpected. Now, very quickly, the theoreticians got to work and tried to figure out what that meant. Let me give you the tail of the tape now for the entire, I'm going to give you everything. I'm going to put all my cards on the table. This is 4 decades later, today, we now have the net result of 3 close flybys of Saturn. 3. Pioneer 11, which is 1979, Voyager 1, 1980, and Voyager 2 in 1981, each benefiting from what was learned from the previous one. And then we have this unbelievably successful flagship orbiter, Cassini, which spent 13 years in very tight, very precise orbit around Cassini. It was just amazing from 2004 to 2017. That's 4 dedicated spacecrafts, and especially Cassini, resident, living in the Saturn orbit for 13 years with its gorgeous magnetometer doing all that work. And the best of those 4 has been to establish Saturn's external magnetic dipole tilt as not exceeding 0.007, which is not sufficient to establish a rotation period. And that's it. We have given up on doing this the magnetic way, which is the modern way that you do it for gas giants. It's called the System 3 rotation period. And we have it for Jupiter down to a second or less. We have it for Uranus. We have it for Neptune. But for some reason, Saturn is violating Dowling's theorem. It's impossible, we were told, theoretically, to actually have this happen. And yet, Saturn basically has no tilt. It's less than 0.007 degrees, which is just vanishingly small. What's going on? Well, the theoreticians, particularly led by Dave Stevenson, that's Davidson, I spelled his name wrong, I have to fix that. It's Dave Stevenson, in 1980, that's terrible, I did that. Let me give a couple of quotes. This is 1980, so it's right after the Pioneer 11 mission came by. Attempts to understand the magnitudes of planetary magnetic fields are an endless source of amusement and frustration. I love it when a very serious scientist doing very heavy work is able to step back for a minute in the middle of his paper to Science or Nature and make a very truthful statement. Attempts to understand the magnitudes of planetary magnetic fields are an endless source of amusement and frustration. But he found an inhomogeneously, stably stratified metallic fluid layer. Now think about it, hydrogen is what these planets are made out of. And hydrogen, if you look on the periodic table, is an alkali metal, like in your battery, like lithium, right above lithium. And you don't think of it as a metal, but if it's under enough pressure, it becomes a metal. And these planets, Jupiter and Saturn, have enough pressure that they're mostly metallic, shiny silvery metal, metallic hydrogen. The hydrogen is an alkali metal, it's turned into a metal. And so an inhomogeneous, stably stratified metallic fluid layer that's very conductive, it's metallic. Above the dynamo region is in differential rotation. because of the equator to pole temperature difference. This flow tends to make the external field axisymmetric. What he's saying is that the dipole is operating as Coulomb requires. It does have a tilt. The self-sustaining dipole does have a tilt, but the overlying that is a differentially rotating electrically conductive layer that is spinning at a different rate, and that kills all of the, just absorbs and shields all of the tilt of the magnetic field, and all you get left is what is parallel to the rotation of that differentially rotating layer. So Stevenson, several did that. Dave Stevenson saw this actually in 1980, and of course this has been verified and confirmed. So basically that's the idea right now, and this goes back surprisingly to Lowell's idea that you had this incredible rotational going down in depth with respect to radius as you go into the planet. And I still don't understand his insight there. I'm not sure if it's actually physical, if it's just a coincidence or not, but it just is uncanny now. But we have this Saturn as a fact, that there is no tilt to the dipole, and we think it has to be tilted on the inside and is shielded. Okay, so that's what we think is happening. So this is not happening on Jupiter, and so what we're learning is, the most fundamental takeaway I think is that the inside of Saturn and the inside of Jupiter are very different dynamically. There's a lot of space inside these planets, and there's a lot going on, and Saturn and Jupiter are fundamentally different in what's going on inside them. Stevenson concludes, the differential rotation causes rapid radial attenuation of the non-axis symmetric parts. This is consistent with the Pioneer 11 observations. So the magnetic field gives us strong information about the fact that there's huge shear inside. And so there isn't really one number. There is a number, there is a bulk number for Saturn, but it's turning out to not be very important because of the enormous shear, depending on where you are with depth. Okay, but we still, in atmospheric dynamics, which is my field, and also with magnetic studies, we still need to know what is the bulk rotation. We need to know what the zero is for the winds, because that's the way dynamics works. So we have to get a number, and the International Astronomical Union, the IAU, needs to put out a number for each of the planets, and they have a committee that does that. I'll show you their latest report. So the fallback plan, since you can't see any mountains because it's a gas giant, there are no mountains. Like on Mars you can see mountains, in Venus you can't either, but you can with radar. But on the gas giants you have to go there with a spacecraft and use a magnetometer. We've sent 4 spacecraft, and we've failed utterly to detect any rotation period from the magnetic field, except it looked like there was there. It looked like if you backed up to a sort of a plan C or a plan D, depending on how you're counting, there was something called the Saturn kilometric radiation, the SKR. This is a radial period, and it was fairly darn periodic. And if you averaged over time, and we've got a lot of time, because remember, these spacecraft, they have a far encounter sequence that lasts for months. And we have now Pioneer 11, we have Voyager 1, and we have Voyager 2. That's a lot of data. And they were able to get a period out of that, and they even put a pretty small error bar on it. And the value that they got was, this is now, and this is today, during this talk, I mean right now, this is the official, discredited, this is the official International Astronomical Union value for the number we're talking about in this talk. 10 hours, 39 minutes, and 24 seconds, please, 24 seconds. It's crazy when you have uncertainties, measured in minutes and multiple minutes, and you have that kind of precision. But that's what people use for the rotation period of Saturn. And for various applications, if that's off by even a few seconds or a few minutes, it depends on what your application is, that's disastrous. But you can see how it's consistent with some of the earlier things. So this is what was measured here, and we're now bumped up here from the original line, which was way down here in the 1016, 1014 region. We're jumped way up even past this 1038 that we got with the up here in the early 1900s to the settled value, the actual world's official value for Saturn's rotation period, 10 hours, 39 minutes, 24 seconds, based on Plan D, based on the backup plan of using the SKR radio signal. So that has been, since the time of Voyager, which was the early 80s, that has been the number to define everything, to define the longitude, define the rotation. Now let's get into the current century. Now we're into the 5th century of this discussion. We started out in the 17th century, then we went 18th century, which didn't have very many spots to track. Then the 19th century, which was incredibly active, brought in spectrograph, things like that. The 20th century, which of course some of us have lived through. And now we're in the 21st century, and Cassini started its mission at Saturn, arrived at Saturn in 2004, and it was a 13-year mission. Cassini discovered that this SKR, this Saturn kilometric radiation, this radial period, slips like a clutch. 8 minutes. It's just, remember, you can't even imagine a planet of this magnitude rotating for this many billions of years to change even a fraction of a second. Maybe a few seconds if it had some huge, huge event that changed its moments of inertia. But not 8 minutes, not 10 minutes. Cassini discovered that the SKR period slips like a clutch and is different in the northern and southern hemispheres. It is just a magnetospheric outer measurement. It's really very poorly coupled to the actual bulk of the planet. This is the data versus time. Now look at this x-axis here. We're talking years, 2004 through 2011, and this is the rotation rate of the SKR periodicity. And you can see there's actually two components, and this was devastating. This is Gurnett and his colleagues to discover that this signal that was being attributed to Saturn's internal bulk rotation was actually just a magnetosphere period that was just playing piggyback and slipping like a clutch, and the north and the south couldn't even agree. Where does the official time go on this? 10 hours, 39 minutes, and seconds is this line. And if you have to go back to Voyager, which is over here, you know, to 1980 and 1979 for Pioneer, and you get that line. So you can see what's happening. This is the south component, and this is the north component. They actually cross just after equinox, when Saturn is going through equinox. So this is not Saturn's rotation period, and yet, even to this day as I speak to you, this is what we are basing Saturn's rotation period on. We have got to get away from this SKR, and everyone now knows it. It's just where you go. Okay, so I want to draw your attention to this number that I told you that was our convergence number. This 10-hour, 34-minute number is right here on this green line here. And what you can see is it looks like it's literally a clutch. So in other words, the magnetosphere is got some loading on it, and it's sort of sluggish. It's got some inertia on it, so it can't keep up with the rate. It's being dragged by the planet, the number that we want, but it can't keep up with it. It keeps slipping. So it keeps going to a longer rotation period by several minutes, by 5 minutes. But when it gets as locked so that the clutch isn't slipping, it gets as locked as it can be, it actually brushes up against 10 hours 34 here. So that's sort of indirect evidence that there is an internal rotation period that's a good 5 minutes faster. And remember, faster, that means the mass is concentrated more towards the center. It has huge implications. All right, so this brings us up to, let me first show you the International Astronomical Union, the IAU, how they do their work. It's done by committee, of course. And this is the report of the IAU Working Group on Cartographic Coordinates and Rotational Elements, 2009. And I know some of these people. Michael Hearn here, the second author, he just passed away recently. This is, it's very deliberate work. It's very carefully done, and they're very conservative. And I just quote from this paper, recent Cassini observations are about 8 minutes longer. It actually went all the way up to 10 hours, 45 minutes, that SKR signal. Then recently determined period, it appears as if the rotation period cannot be obtained reliably from Cassini magnetic field observations alone. What plan are we on now? Plan E? Just this planet, oh my gosh, since the 1600s we've been trying to get this simple number, the rotation period of Saturn, so we can do things, so we can learn about the interior structure of the planet, so we can put it on the map with all the other planets and figure out what's going on. And we have not done a whole lot better than Herschel in all of these 5 centuries. So what can we do? 4 centuries since Herschel. Well, what we have now is that 10 hours, 34 minutes, 24 seconds is not Saturn's rotation period. All right, so let's bring this up to very recent history. We're talking since 2009 here, and this actually is personal for us. This is work that's done here in Louisville, and also with collaboration in Oxford at the University of California, Los Angeles. First, there was an idea in 2007. You can see I'm on the last 3 dates of my timeline here. In 2007, Jerry Schubert and his colleagues worked on a model that included gravity data and planet shape data. They also incorporated the wind data that they had, and they got 10 hours, 32 minutes, and 35 seconds. Quite a bit slower than the official time. And that was, of course, controversial at the time. Came down all the way to here. Now, the problem with this, in my opinion, and some of my colleagues' opinion, is that it's really not strongly coupled. You really need your signal to be clear. You need it to be connected. It has to be actually connected to the internal rotation period of the planet, and it needs to be calibrated. And this one is a clear signal. All of the signals being used here, the gravity data, the shape data, are very clear, give or take. but they're not connected, and I would argue that they're not connected directly to the planet because the planet does not have to obey the assumptions that were made in this study. This was just an optimization based on several model assumptions, and I think that, for example, if you include too much of this great equatorial current, you can get biased too fast. Remember, the great equatorial current is, as Herschel and Hall and the others, Keeler, measured, it's more like 10 hours 16 minutes. And so you can't contaminate the bulk rotation period by getting too much of that. And so it's a very difficult measurement to make. So 10 hours, 32 minutes and a half, but you can see that even though I'm a little skeptical that that's actually connected directly, it's connected indirectly because it's coming really close to two other very independent observations. The next one, which brings us to the second to the last day, is, you can't see it on the screen here, but I'll read it to you. New wave methods, starting in 2009, that was pioneered by the University of Louisville here to today. We now know that Saturn's interior has large mass anomalies that perturb nearby wave-bearing fluid regions in a conspicuous manner. Here's a schematic of Saturn. And what we have is the interior of Saturn, remember, is much more active, it's just crazy, doing things that Jupiter is not doing. There's some amazing things going on we're just getting a glimpse of in the interior of Saturn. But fortunately for us, that activity, that mass anomaly activity, that great churning and structure that's inside of Saturn is perturbing wave-bearing fluid regions in a conspicuous manner. And those wave-bearing fluid regions are the atmosphere and the waves in the atmosphere and the inner C ring. This is the A, B, and C ring and the inner C ring. And if you look, those are the two fluid regions that you could see waves in that are closest to the mass anomalies in the interior, right at the edge of the planet and right on the inner edge of the ring, across this gap here. And of course, the Cassini proximity orbits actually went in between there 26 times. That's where we get all the data for the gravity field. So the new method or the new philosophy for figuring out Saturn's rotation period is to base it on waves that you can measure. And the first idea was to look at the atmospheric waves. That's the work that we did here in Louisville in collaboration with Peter Reed at Oxford. And we got a value of, it's cut off, we got a value of 10 hours, 34 minutes, 13 plus or minus 20 seconds. And that is actually shown here on the 2009 plot, like that. And that's a paper is Reed, Dowling, and Schubert from 2009. And then if you go 10 years later, which is 2019, just last year, we have a very exciting result, completely independent. And this is what a new field of science called chronoseismology. Now we have seismology, that's looking at the waves from earthquakes to figure out the interior structure of Earth. And for astronomy, we also have helioseismology, which figures out the internal structure of the sun. And now they do stellar seismology to figure out the internal structure of stars. It's incredibly accurate. You can model the interior structure based on the waves that are propagating through these bodies. And you just look at the surface waves very accurately and you can get the interior. That's seismology. Now that has always been a dream for the giant planets, but the signal is so hard to see. What was realized, and Dave Stevenson again was one of the ones that realized this, is, and others, that if you were able to measure waves in, these are called bending waves and spiral waves, in the rings, particularly the ring that is closest to the planet, the inner C ring, if you were able to see waves in there, they may not be perturbed by satellites embedded or outside the rings like almost all your waves are. There's lots of waves in Saturn's rings, and they're very accurately measured now by Cassini. But if you're close enough in the right place, the satellites don't have the perturbations, it doesn't line up. The resonances are coming from the planet itself. The mass anomalies inside the planet would create waves. In fact, it's been argued that Saturn's rings, which we know from all of those arguments before, is made up of little ice chunks, little small ice chunks, just millions of them. That we know that any waves that you would see there would give you a seismograph more sensitive than any seismograph that we have. Saturn is an incredibly sensitive seismograph, very exciting. So this is a completely independent way. Now what's happening is the mass anomalies are using the two classical kinds of forces. If you remember taking a freshman physics course, you have body forces, which are like gravity and magnetism, and then you have surface forces, which are like pressure. Well, the mass anomalies are using pressure to affect the atmospheric waves. That's the study I was a part of. And the mass anomalies are, in addition to using surface forces like pressure, are using body forces like gravity. to reach out through the atmosphere, through space, and to perturb the C ring. And they found over 4 dozen of these waves in Saturn's C ring, and they get a value of 10 hours, 33.6 minutes with a huge error bar, about a 2-minute error bar, plus 1.9 minutes, minus 1.3. So our measurement, the measurement of the atmospheric waves, the 10 hours, 34-minute measurement with its error bar falls inside the error bar for this chronoseismology. Chrono is a prefix that just refers to Saturn. So this is a kind of a convergence, but I want, this is Mankiewicz et al. Came out just last year, 2019, and of course that's the first of many papers that will come out. This is a new field, chronoseismology, and they're going to have new results every few years. But we do see, at least we're trying to talk ourselves into a kind of a convergence here of 10 hours and 34 minutes, where we're plus 13 seconds and the chronoseismology is minus about 20, 40, somewhere in there, 20 seconds or so. So if you average the two and just round to the nearest minute, which I think is all we're allowed to do with this kind of precision, 10 hours, 34 minutes is what these two are doing. And then even the 10-hour, 32.5-minute one from the shape analysis is in that same block. You can see we're trying to converge here. But if you step back and look at the 5 centuries of this discussion, it's only this little. I've been twiddling my thumbs literally for 11 years, since 2009, waiting for anyone else to come up with a number to either confirm or refute, right? And we got beautiful confirmation. Whoa, right? I'm excited. 11 years, that's a third of my career, right? It's just little blip on this, when it goes there. So who's going to be convinced by that? We have to wait how many more centuries? It's crazy. So Saturn is very difficult, and at the end I'll basically say we still need a little more data. We need to put some probes into Saturn, just like we did for Jupiter. Okay, so I'm going to conclude here and go to a final slide, some thoughts that Dave Simpson shared. He's the head of the interior modeling team that's working with both the Juno data at Jupiter and the Cassini data. So finally, from Cassini at Saturn and Jupiter, Juno at Jupiter, what are the latest interior modeling ideas that are coming from this very exciting time where we have, for the first time, we have the gravity harmonics and the magnetic field spherical harmonics from both of these planets. What are we getting out of that? So this is a 2020 status report for Saturn's interior. A summary of thoughts from the interior team leader, David Stevenson. I did spell his name correctly here at Caltech. And the first point is an accurate rotation period for Saturn improves understanding of Saturn's magnetic field and atmospheric dynamics. No question. The shape, gravity, atmospheric wave, and C-ring data analyses, those things that have been happening since 2007, 2009, and 2019, are starting to converge. Relative to the history of this topic, maybe we need to wait a little longer, but they do appear to be converging. Second point, Saturn's even harmonics of gravity reveal very strong differential rotation in depth. Back to Lowell's idea, which just knocks my socks off. I don't know what Lowell was thinking. I have to dig into that a little longer, but wow. So we're getting now from the wonderful data from the Cassini proximity orbits that that the interior of Saturn is messing with the even harmonics. This was not expected, and there's enormously strong differential rotation, but we know that the differential rotation has to be there just to get the magnetic field wiped out so that it has no perpetual tilt in the external. We know there has to be some differential rotation. So the magnetic field is going to be as equally important as the gravity field as this is worked forward. This is work in progress. This is very exciting. People are working on this right now. For interior modeling, an accurate rotation period is now less useful than originally expected, even when they designed the Cassini mission. Less useful. And that's due to this surprisingly large differential effect. And this is work by Ravikali and colleagues, basically saying you can be off by a minute, a couple of minutes, and it doesn't really affect what we're doing to try to understand the interior rotation, because the rotational effect, the differential effect, is so large. There isn't a rotation period for Saturn when it comes to interior models. There's an average bulk period, and we need it for the atmospheric dynamics work, but it's just not a constant, it's not a solid body rotation until you get incredibly deep inside the planet. Nobody really was expecting that. We expected some differential rotation. Remember the Pioneer 11 result that there was no tilt? That was not expected. Very quickly was rationalized, but it was a surprise. And now we have all this other evidence that there's a huge mass anomalies inside and there's enormous differential rotation. What a fascinating interior if we could only get in there to see it. And that's really the last point here, the last point of the talk, is we need atmospheric probes to get under those clouds, in situ probes and to measure the winds below Saturn's clouds, hopefully at multiple latitudes, incorporating the design lessons from the one and only gas giant probe we've ever put in, which was the Galileo probe that went into about 6.5 degrees north latitude on Jupiter. So we've had one probe and it was successful for one probe. I can imagine trying to predict the weather on Earth with a single sounding. It's ridiculous. So we need to get under those clouds with in situ probes, and that's part of the thinking, what we call the decadal survey and the future planning. We've got to get in there, and we've got to learn from what we did and didn't get out of the Galileo probe to make an even better mission to Saturn. And that's where we're at right now. All right, thank you very much for your time, and I'll take any questions if you have any. Thunderous applause that we'll put in later. Ethan?
Mass anomalies. That'd be something.
Well, we have a microphone. Let's do the microphone.
Hello?
There we go.
You're saying mass anomalies, obviously on the surface. Would that be something, say,
No,
like,
in the interior.
Oh, in the interior. So would it be something like mountain ridges coming in contact with wavefronts, or?
Good question, but there are no, this is a gas giant, and in fact, the bulk density of Saturn is well known. It's less than 1. It would float in water. So there are no mountains. There's no solid surface. Maybe the size of Earth, maybe a little, an almost negligible core at in the center. So you think fluid all the way in, basically metallic hydrogen, liquid metallic hydrogen all the way in. So we were talking about waves here. These are great big churning, more like a very stormy ocean kind of topography and mass anomalies that we're talking about. Good question.
So with that, it was a chronoseismology or chrono?
Chrono, it's K-R-O-N-O, chrono.
So do we know, like, what is causing the effects? Like, is it something forcing it to slow down and causing seismic effect, or is it just unbalancing causing the seismic effect?
If you have highs and lows of pressure, then the highs basically are more mass and the lows are less mass, and that's enough. It's very subtle, but that's enough gravity for something as sensitive as a ring particle in orbit in Saturn's rings. Incredibly sensitive. They are actually sensitive to their own self-gravity. Can you imagine the ice cubes in your freezer being sensitive to each of their own self-gravities? That's what's going on in these rings, and they're incredibly sensitive. And nothing else besides this is perturbing them at that particular inner sea ring. And so that's what's happening. But yes, they're going to figure it out eventually. But that model, that first model, that's actually a lot of work to come out with, that 2019 model, the first chronoseismology publication, is actually assuming that the interior of Saturn is solid body rotation, which from all the evidence I've been talking about all during the talk is clearly not the case. But that's their starting point, so it's a fairly crude model. That's why they have 2-minute error bars on it. So we have to take that one with some patience. But those are going to get better. The models that are connecting the beautiful observations, there's over 40 of these waves that have been detected in Saturn's sea ring, the inner sea ring, that you can very definitely rule out that they're being caused by satellites like Mimas and the other satellites. Can't be. It has to be coming from Saturn, from inside of Saturn. And so yes, I think in the next 10 to 20 years, we're going to get some interior structure of Saturn from the chronoseismology and also from the magnetic field and the gravity field. Right now, the signal is just incredible. They didn't expect this, well, maybe we should have because of the 800-mile-an-hour equatorial jet, but inside it's like that too. There's this huge shear on the inside. And so I think we'll eventually start eliminating parameter space and start to narrow it down. But it's a very exciting time right now because it's just completely open. And we do have good data. I mean, the Cassini proximity orbits are good data. And there's a feeling that the magnetic data, which is a little messier and more difficult to work with, has some really key independent information in it. When you put that together with the gravity data and what we're seeing in the atmosphere above and what you're seeing in the rings, I think we're going to get a much better picture, but it's going to take a little while. And that's where we need the grad students to get in there and work on this. Thank you.
Hello. So you were talking about a equatorial jet stream. Is that the only jet stream that exists in the atmosphere of Saturn? Does it dissipate near the poles, or are there polar.
Right, so it isn't, there are actually a dozen or more than a dozen jet streams on both Saturn and Jupiter, and that plot, that plot that was the orange and red, the Cassini plot, that actually, all of those wiggles, each wiggle is a jet stream.
Okay.
And so, yeah, it's dominated by that crazy equatorial jet stream. And now on Earth, it's very different. We have a slightly retrograde equator. So our equator kind of is a little slower than average. But on Jupiter and Saturn, it's roaring in the other direction, especially on Saturn. And then you get to Uranus and Neptune, and it's retrograde again, like Earth. And Neptune, crazy retrograde. So, you know, it's just crazy. It's fascinating. It's called the zonal wind problem, zonal meaning east-west. And the fact that we have dozens of jet streams instead of just, say, 2 like Earth has, it's a fascinating thing. Basically, it's bigger. These planets are much bigger. The length scales, the intrinsic length scales in the atmosphere is about 2,000 kilometers, just like on Earth, in Earth's atmosphere. But the planet, like Jupiter, is 120 times more surface area than Earth. So you take these jet streams, these 2 jet streams that barely fit on Earth, and you give yourself 120 times more surface area, linearly dimension 10 times more, and you just have a huge playing field. And it fills up with jets, alternating east and west and east and west. And it's both Jupiter and Saturn. And the rotation rate, of course, if you're flipping it back 5 minutes and 10 minutes, like you're completely changing the jets in meters per second. And so at the time of Voyager, when they settled on that 10-hour, 39-minute thing, all of the jets were then prograde. And one of my mentors, Rita Beebe, who's one of the grand dames of astronomy working in Jupiter on the Voyager mission, she said to her colleagues when she worked this out, she took the 10-hour, 39-minute, and she got the jets in miles per hour, meters per second. And she said, "My winds are spinning up your planet." It's one of my favorite quotes from her. "My winds are spinning up your planet." And it just didn't look anything like Jupiter. Jupiter has a nice alternation, westward, eastward, westward, eastward. And so when we refine that and come down from 10 hours, 39 minutes to 10 hours, 34 minutes, it's a huge 5-minute change. It changes those to be beautifully Jupiter-like. So now if you use that rotation period, it does, in fact, you have eastward and westward alternating just like Jupiter. So it looks like using the Voyager value, which is, again, still the official IAU value. It needs to be changed desperately. But changed to what is the question? But it's just throwing off the atmospheric dynamics. Because people do models, they're saying, our models are getting jets, but they're alternating. We can't get all the jets to go prograde. The angular momentum just is totally messed up to do that. And so there's a lot of lines of evidence to say it has to be faster than the official value. And it's about 5 minutes faster. So we're really starting to get a little bit comfortable with 10 hours, 34 minutes. But and also the fact that you really don't need, for some of the interior work, you don't need it better than that. You could round it to the nearest minute and it'll be fine. That's a surprise. When they went into the Cassini mission, they really thought they were going to need it down to a few seconds because of just the way interior models work when they're sort of static on the inside. They don't have anything but a static interior for Saturn. It's amazing what's going on inside there. We could just barely get a hint of what's going on. But I think there's a lot of exciting developments that will come as we go forward with this new mindset of all that can be going on inside these giant planets.
Awesome, thank you.
Any more questions? I have one. So we know Saturn's a little special because of the beautiful rings, and we now know that the interior of Saturn is a little special.
Right.
Could they have a common origin? Could they have is this something that could?
Well, the rings have been dated by how much dirt is on them. And this is a result that's only come out in the last few years. And the rings of Saturn were either old or young. And as Cassini was collecting the data, they would tell us, it's old if this happens to the data, give us this value, it's young. And the data came out young. Young, like 100 million, 200 million years. Just a fraction of a billion years out of the 4.5 billion. So the rings of Saturn have only been around, you know, the biosphere on Earth is much older than the rings of Saturn by quite a bit. So that's interesting because that's uncomfortable. How do you basically have to take an icy satellite like Venus and just shatter it, and then you can make that. So there was actually around that same time in the Earth geological history one of the major event horizons, one of the major extinction horizons. So this gives me the chills. I don't know about you. What did we go through? What did the solar system go through that killed off almost all the species on Earth and gave us the ring on Saturn on the same day? I mean, maybe, or you know, not very precise, but it's interesting to think like that. So I think the rings of Saturn are now thought of as a sort of more recent, and they are eroding fairly quickly. So it's beautifully lucky that we have this seismograph out there. The mass anomalies are just something to do with Saturn. And now one big difference between Saturn and Jupiter is Saturn's quite a bit less dense. quite a bit less dense. Jupiter is more than would sink. Saturn would float in water. And so, but that's sobering because they are very similar in size. You know, that was expected because if you have metallic hydrogen for your interior, you kind of all have the same size. But these details and the lack of tilt of the magnetic field and these anomalies, the atmospheric waves and the ring waves, it's just incredible. It feels like it's going to come together, right? We're just at the beginning of this. And I'm comfortable with the amount of data that we got, especially from the Cassini proximity orbits, that we're going to get somewhere with this. But I think what ultimately we're going to have to do is go back to Saturn and put some probes in. Like the Galileo probe, but I think we need more than one probe. And the Galileo probe was 6.5 degrees north latitude. It wasn't even outside the equatorial tropics. And so we really need to get into what, remember those spots that showed up at the high northern latitudes that had a completely different rotation period. We need to get up into the mid-latitudes and get some probes down under there. There's all kinds of interesting ideas for probes. There's the probe like Galileo with a big heat shield. There's also ramjets, nuclear-powered ramjets that use the hydrogen actually in the atmosphere and fly around. There's all kinds of interesting ideas, but we need to at least get a couple of maybe heat shield type, sort of Galileo probe type observations under the Saturn's clouds to really get some ground truth for this topic. But I think even without that, we're going to make some progress over the next 10 to 20 years.
You're planning something with Titan, right? The mission to Titan.
There are missions to Titan, of course, fascinating because it's got a wet hydrological cycle. It's the only other planet, you don't want to call it a planet, it's bigger than some of our planets. And it's got a hydrological, it's got rain, it's got lakes, it's got streams. So it's fascinating in that sense. Titan is just a wonderful, I mean, its atmosphere, this moon's atmosphere is 1.5 bars. It's actually 50% more pressure on the surface than we have on Earth, which is crazy for a moon. So this mission going back to Titan is going to be a drone called Dragonfly. That's a really exciting mission. That's going to be really neat. Nuclear-powered drone on Titan. But also the icy satellites, of course, and the idea of habitability, what we call ocean worlds. There are these missions. Some of them are flying, some of them are, cutting metal, and some of them are on the drawing board. But there's a lot of interesting outer planetary work with the icy satellites with Titan that are coming up. But we've got to get back to the planet itself. And politically, you just had this gorgeous 13-year orbit mission, but there was a probe. Cassini had a probe. It was Cassini-Huygens. It was a dual mission. And the Huygens probe went into Titan because of how fascinating Titan is. You basically have one shot at it. And so what we need really is a dedicated mission that will just bring probes, plural, into Saturn and put them in. So we can if we could just get the wind speeds down to several tens, maybe to 100 bars of pressure, then it would revolutionize what we're talking about here. But I think even without that, we're going to make some profound new appreciation and discoveries about the interior structure. And just the diversity of interior structure that you get now just with Jupiter and Saturn. That means all the exoplanets that we're seeing, most of which are sort of Uranus and Neptune sized, are full of this incredible. I'm personally very surprised that you take the largest volume of real estate and say things are happening inside it. Well, of course, it's not a desert down in there. But there's a lot of heat coming up in these things, and there's a lot of churning, and there's an enormous amount of rotational energy. So a lot more going on than anybody had the imagination to foresee.
Thank you so much for your wonderful talk.
All right, thank you for having me.
Yes, we were now clapping, or at least we're doing
We'll type
clapping
it.
emoji. And so I was asked if I could have the winners of the prize front here one more time, so that we all look into the camera. Yes, there we go. So, Emily Spicer for the best paper this year, and Dominic for the scholarship. Thank you to the Marshall Bullitt Fund for funding and supporting us, and for the SPS Society of Physics students for logistical support, and for Drew and the planetarium people for hosting us. So thank you so much, and thank you, the viewer, for hopefully seeing this. So, thank you all. Thanks everybody for coming. Thank you for giving it. Fantastic. I'm happy.